So we're dealing with gas power systems. We've covered the Otto and the diesel cycle. When you think Otto and diesel, think closed system analysis. But the system can expand and then compress and expand and compress. So, but it's a closed system analysis. And then we're going to move today into the power cycle called the Brayton power cycle, and it models both the stationary power plants that burn primarily natural gas and to make electric power, as well as gas turbines for propulsion systems. And there's a number of enhancements that go with the Brayton cycle, so we'll talk about those. But today is just an introduction to the Brayton cycle. So a gas turbine, especially used in a stationary power plant, has a compressor which takes and ingests outdoor air, filter, clean, outdoor air, and it boosts the pressure. And so the pressure at 2 is a factor times the pressure at 1. It's greater than the pressure at 1, and often they specify the pressure ratio P2 divided by P1. Maybe that's 9. The pressure after the compressor is 9 times the inlet pressure, P1. Or maybe it's 10, or maybe it's 11, or maybe it's 12. But it's a pressure ratio. That's a little bit of a tongue twister coming off of Otto and diesel. What was our ratio? Compression ratio, a volume change. This is a pressure ratio. See that? Pressure ratio versus compression ratio. So if I get this thinking fast and talking fast, sometimes I'll slip and I'll say compression ratio for a Brayton cycle when I really needed to say, or meant to say, or intended to say pressure ratio. So often the pressure ratio is specified for these. It then goes through, after the compressor, goes through the combustor. In the combustor, its fuel is added, and there's a fireball. And it's continuous flow through the compressor, through the combustor. The pressure change through the combustor is negligible, so often P3 is equal to P2. That's our assumption. In a real system, if you have flow through a duct or through a pipe or through something, there are real friction effects and there will be a pressure drop or pressure loss. But here, P2 is assumed to be equal to P3. No pressure loss through the combustor. Now, think about this for a minute. What about the temperature at 3 compared to the temperature at 2? It's much greater than the temperature at 2, okay? So temperature at 3 is much greater than the temperature at 2. Now here's something. What about the volume occupied by 1 kilogram of air at 2 compared to the volume occupied by 1 kilogram of air at 3? It's much greater at 3, isn't it? The volume occupied by 1 kilogram of air at 3 is much greater. Why? Because it's spanking hot now. It comes out of the... It's not a different pressure. It's a different temperature. So this is much greater too. V sub 2. So now you have a large volume, think about that, or a large volumetric flow rate of hot gases, and they're at high pressure, and then they can really expand even more as it goes through the turbine, and it drops the pressure. P4 is back to P1. It's back to atmospheric pressure. So now the specific volume at 4 is much greater than the specific volume at 3. It expands some more, primarily because of the drop in pressure. But as it's expanding, it's pushing the blades of the turbine, and it's doing work on the blades of the turbine, and it produces power. So we have the work per unit mass out of the turbine. The compressor, there's a number of ways to write it. You can do this. You could put the work coming out of the compressor, and you know that this has to be a negative quantity because a compressor is not a work-producing device. That's staying with the sign convention, or sometimes you just abandon the sign convention. True? What about the combustor? That fuel is coming in and it's burning. There's a large heat release. True? That's how you get much higher temperature coming out. What comes out at 4 is the nitrogen, which came in, which the air comes in around 20% oxygen and 80% nitrogen. So it's still 80% of the nitrogen. All that nitrogen comes out, but the oxygen was mixed up with the carbon, hydrogen, fuel. Maybe it's methane. CH4, is that methane? CH4? Yeah. So it'll come out as CO2 and H2O, and maybe just all of the oxygen was consumed in going into the CO2 and the H2O. So it'll come out as carbon dioxide and water vapor. Okay? But a lot of nitrogen still. Well, this system is the way it really happens. There's also some other enhancements to the basic gas turbine, but compressor, combustor, turbine, and what we want to do is we want to model it, so we will close the loop and we'll replace this complex changing of the fuel with the air, that combustion. We'll just replace that by a heat addition in a heat exchanger, and then we'll just have clean air go all the way through and close the loop, come back around this way, and have another heat exchanger. So the way we analyze these gas turbines is with an air standard Brayton cycle. So what's it mean? Is it's always air, it's never converted to carbon dioxide and water vapor. It always behaves as an ideal gas. Those three things you remember as an ideal gas. What's this first thing? Ideal gas equation. What's the second thing? Internal energy is a function of temperature only, which at first time you think, why isn't it a function of temperature and pressure like steam or ammonia or refrigerant? It's an ideal gas. And then what's the third thing? The enthalpy is only a function of temperature. It's not a function of temperature and pressure. It's only a function of temperature. Okay. Now the combustion process is replaced by that heat transfer, as I described, from an external source. And the exhaust here and intake here were replaced by a heat transfer to an external source. Depends how you want to do it. You can put a couple things here. You could put that as an in, and you know it's going to be a negative in. Just like you put the work out of the compressor, and you know that's going to be a negative out work. But the turbine is positive work out, and this is a positive heat transfer in. Okay. So there you go. There are our states. State 1 is the traditional state going into the compressor. Often they specify the temperature at 1 and the pressure at 1 are given. Often those are given. Then they specify the pressure ratio, P2 over P1 is often given. So you can now calculate P2 as the product of the pressure ratio times P1. And also they specify the maximum temperature is often given, and that's T3. And often that's from metallurgical considerations. From a thermodynamic point of view, the higher the T3, the better it is. But you have to pass really hot gases into the turbine, and the metal materials in the turbine, even if they're exotic materials, even ceramic or other things, still have to withstand those high temperatures and hold up in a harsh environment. So you specify the temperature, max temperature, the pressure ratio, the inlet temperature, and the inlet pressure, and then you can do a lot in the way of calculating the performance of this system. Let's sketch it out on a PV diagram, or sketch it out also on a temperature entropy diagram. True? What does the process from 1 to 2 look like? If it's a compressor, air standard, we're going to have the compressor's adiabatic, the compressor's reversible, so it's isentropic compression. So maybe that's in first from 1 to 2, isentropic compression, 1 to 2. Okay. What's that look like on a PV diagram? Usually the PV diagrams aren't as useful for the Brayton cycle, but you could sketch it. Let's finish out the TS. What about the process from 2 to 3? What do you have? You have pressure is equal to a constant, heat addition. True? And so it'll be like this. Pressure is equal to a constant heat addition, and then you get out to the max temperature at T3. Then you expand it through the turbine to 4, and then back again. True? Is that true? All right. If you wanted to, 1 to 2 to 3 to, okay, now this is the challenge, 1 to 2 to 3. Where is state 4? Where is state 4? And one of the keys is to think about what's the difference in the pressure at 1 versus the pressure at 4. They're equal. So where is state 4? There's, there you go. There's state 4. That was right, to the right of 1. Okay? So there you go. If you want to, we can emphasize that this work from 1 to 2 is the work of the compressor. 2 to 3, you have heat in, Q in that heat exchanger, Q in. Lowercase q, uppercase Q, whatever you want, Q in. What about 3 to 4? You have the work of the turbine. So this is the work of the compressor going in. If you want to have them all positive, then this is the Q out. Depends how you want your sign conventions to be. So if I take a look and say, okay, Q in, I do a first law. It's always nice to draw a little dashed line saying, hey, there's my CV, my control volume. I'm going to do a first law analysis around that heat exchanger to get an expression for lowercase q in. What are the units on lowercase q in? Kilojoules per kilogram. So I'm talking about specific heat transfer. Okay. I know that you can start with the most general form of the first law. The rate of change of energy in the control volume with respect to time, the rate at which it's flowing in with the heat minus the rate at which it flows out across the boundary of the control volume with shaft power, plus the mass flow rate, and it brings in enthalpy. Here it's coming in enthalpy 2, going out enthalpy 3, and then it brings in its kinetic energy 2, going out kinetic energy 3, bringing in potential energy 2, taking out potential energy 3, close parenthesis, and you say negligible changes of kinetic, negligible changes of kinetic, steady state, no shaft work going across the boundary of a heat exchanger, and we're left with lowercase q in, that's cap q dot divided by m dot, is equal to, look at that, h3 minus h2. True? So this is H3 minus H2. Let's do the same thing for the work out developed by this turbine. Is that going to be H3 minus H4? Okay. Here, now because I've drawn this out, I want to now abandon this and say I want to talk about a positive Q out. Okay, so a positive Q out, what is that equal to? Take it slow, draw the control volume, blah, 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 blah. But it's going to be H. Is that right? Good. Now, if I would have left the Q coming into that bottom heat exchanger, then I'm looking for a negative quantity. Switch them. All right. Now I'm going to do this too. I'm going to let this one be a positive work into the compressor because that's what I've shown right here on this sketch right here. And so the work right here, I'm kind of writing the equation backwards. WC is H2 minus H1. Let me ask a question as you march around this thing. You just think of this. How about H2? Is H2 greater than H1? The enthalpy at state 2, is it greater than? It is. It is. I think if you get that straight. And then how about the enthalpy at 3? Is that greater than the enthalpy at 2? Yes, yes, yes. How about the enthalpy at 4 compared to the enthalpy at 3? It's less. It's less. It went down. And then you have heat rejection out of that heat exchanger. How about the enthalpy 1 compared to the enthalpy at 4? Which one's greater, 1 or 4? 4 is greater, so H1 is less than 4. True? So if you get those relative magnitudes of the enthalpies, it helps you not making a sign error. Okay. Let's solve a problem. So here we have an air standard Brayton cycle operating with principal states given in the table. Determine the pressure ratio, the net heat addition to the cycle in kilojoules per kilogram, so it's a per unit mass, net work, and thermal efficiency and the back work ratio. Okay, here's all our states. Notice that they number our states, and looking at it, this is a low pressure, then it jumps up to the pressure at 2 is the same as the pressure at 3. So it looks like our traditional numbering convention is done. So we have the compressor, followed by the burner, just call it a heat exchanger, followed by the turbine, followed by another heat exchanger to bring it full circle. And we have state 1 as an inlet, state 2, state 3, and state 4. And we can sketch it on a temperature entropy diagram. True? 1 to 2 to 3 to 4, back to 1. 1, 2, 3, 4. This is P equal to a constant, P equal to a constant. Okay. We look at, they give us pressure column, temperature column, internal energy column, enthalpy column, and piece of R column. What is piece of R? That parameter in the air tables. Okay? When we had isentropic processes, accounting for variable specific heats. True? Now, you can sit there and say, okay, I'm going to say that the work of the turbine is out, and that's equal to H3 minus H4. I'm going to say that the Q into this heat exchanger right here is H3 minus H2. Now I have to say, is this Q going out? I'm going to put it as a positive Q out. That'll be H4 minus H1. And this is a positive work compressor in. Work compressor is H2 minus H1. True? So if I want either one of the Q's or either one of the W's, I need to know H's. So why did they give me a column of U's? To see if you knew what you needed and what you didn't need. It's a distractor. You could have deleted it and it wouldn't hurt you at all, okay? But if a student starts to do a closed system analysis for the turbine or for the heat exchanger or for the compressor, and they start using those U's, what type of grade do they get on that problem for the exam? Low, because they were confused about what they were doing. True? So it's legitimate to put in distractors, which mean it's tempting, but it's wrong. So there you go. Again, what are these piece of R's? You can replicate this table, okay? So if you wanted to replicate this table, you could go in there to the air table, and let's say the inlet temperature at state 1 is 310, and you just look up P sub R. It's a function of temperature only. All right, and then you can march through, and what you'll do is you'll use that P sub R to get the state 2 fixed. Because the compressor is isentropic, unless you have some efficiency specified for the compressor, true. And so if it's isentropic, then S2 is equal to S1, hence PR at state 2 divided by PR at state 1 is equal to P2 divided by P1. And you can double check this, and it'll work. It'll work. So that's how this table was built. It was built by getting PR1, multiplying PR1 by the pressure ratio to get PR2, knowing PR2, coming across and interpolating to get H2 and T2. True? All right. Let's take a look at answering the first question, part A. What is the pressure ratio? Is that just P2 divided by P1? Is it just 1045 divided by 95? And guess what? Students say, no, it has to be more work. There has to be some more work. But no, that's the right answer. And what is that number if you do that ratio? It's 11. So you have P2 divided by P1 is equal to 11, and then you box it. This is one of those cases where they could have introduced a symbol like PR as a pressure ratio, but they didn't. They just say, let a pressure ratio is P2 divided by P1. Okay? And that's what you're looking for is equal to what you calculate, and that's how you box the answer. How about for part B? The heat addition for the cycle, this word net is confusing, shouldn't be there. Just what is the heat addition for the cycle? Isn't that lowercase qn? Isn't that H3 minus H2? Notice that this bold, and this bold, true, those are typically things that are fixed. They tell you the inlet pressure, inlet temperature, and the maximum temperature. The maximum temperature of the cycle is at state 3, so it usually is specified. So basically, without repeating it up in the word statement, it's just shown here in the table. So we have H3 minus H2, and when you calculate that, you find that the Qin is 899.9 kilojoules per kilogram. How about for part C? What is the net work? Well, you have work net. You can calculate it two ways. You could say, what does the turbine produce minus what the compressor consumes? You could also say, well, work net is Q net, true? And Q net is equal to Q in minus Q out. Here is the Q in here, and here is the Q out there. Either one will work. All right? So let me see, if I do the work of the turbine, we already have it right here. It's H3 minus H4. And so the work of the turbine is 728.2 kilojoules per kilogram. And the work of the compressor, 305.2 kilojoules per kilogram, giving us that the work net is equal to 423.0 kilojoules per kilogram. And I think it's really helpful if you say, okay, well, is this consistent? We already got Q in 899.9 kilojoules per kilogram. What is Q out in the other heat exchanger? 477. It sure doesn't look like this number minus that number is going to be the same as this number minus that number, does it? But it is. It is. Okay? Good. So that's part C. What is the thermal efficiency of the cycle for part D? Let's put it up here. the thermal efficiency is the net work divided by the Q in, true? And so that just is equal to the 47% for this data. So it's 423 divided by 899.9. And then the back work ratio for part E. The back work ratio. Well, that concept was already introduced for the vapor power cycles. So how much has to go back to feed the compressor of what was produced by the turbine? And so the back work ratio in this case is 41.9%. Very large number. That back work ratio is the 305.2 divided by 728.2. So now this is the reason that gas turbine engines were developed much later in time than steam engines. Those simple vapor power cycles. Those were back work ratios 1-ish, 2-ish%, true? And so you could have a lot of inefficiencies and the thing would still run. If you have some inefficiencies in the compressor and some inefficiencies or irreversibilities in the turbine, this thing quickly stops working because it has such a high back work ratio. Okay? So there you go. But if you get the compressor to run well and the turbine to run well, this is a great power plant. It produces a lot of power for little weight of the equipment. And that's why they use in flying machines, in helicopters. Gas turbines are the primary source of power in helicopters. Tremendous power, low weight. Jet engine, exactly. Now, we just talk about right here for stationary power plants, but okay. Here are the data for this problem in case you want to check it later. Here is the Excel file used to calculate everything. You can see the pressure ratio. You can see the Q's, 2 of them are 0. You can see that I stay with the sign convention even though the one I was just solving for, I said I'm going to treat that as a positive quantity. Calculated Q net, calculated work net, calculated the efficiency, calculated the back work ratio, all in Excel. Okay. The air tables are implemented in Excel, and so you can call that PR. I think the call in Excel is PR_T for temperature _air, and then you have to feed it something in Kelvin, the temperature in Kelvin, and you'll get the PR. That's built into the Excel tables that are available in the computer. This was not downloaded from the University of Alabama. That's not from them. It's what we generated here with student help before.
What's the other percentage right next to the efficiency and the back work ratio?
We're going to have an equation assuming cold air standard analysis, and that equation gives us the thermal efficiency only a function of the pressure ratio, and that's what that equation predicts for this pressure ratio and 1.4 for K. And that's just a quick comparison. It's in the ballpark, but it's not spot on. This accounts for variable specific heats. Okay? So when you have that additional assumption of constant specific heats, you go back and remember, okay, I'm dealing with ideal gases, constant specific heats, and if it's an isentropic process, there's 3 equations that are very, very helpful. How pressure changes can be related to volume changes, temperature changes to volume changes, and these were used a lot for the Otto and the diesel cycle, were they not? Because we talked about what type of ratio? A compression ratio, which is a ratio of volume changes. But when we talk about the Brayton, we talk about a pressure ratio. And so this is how the temperature changes for changes in pressure. So that works. This equation is our favorite equation for the Brayton cycle because it's a pressure ratio going up across the compressor and the same pressure ratio, but it's going down across the turbine. So you'll see this T2 over T. So if I wanted to, I would say, here is the compressor. You're going in at state 1, you're going out at state 2. The temperature at 2, assuming isentropic compression, is the temperature at 1 times the pressure ratio, P2 over P1, to the K minus 1 divided by K. Right? And then if you come over to the turbine, and you have state 3 coming in and state 4 going out, the temperature for isentropic expansion from 3 to 4 will be the temperature at 3 times 1 over P, oh boy, I got to get this right, 3 over P4 to the K minus 1 divided by K. One way to look at that equation is to say, just kind of turn it around conceptually. Think about going that way from 4 up to 3, and you get the right. It's like turn this equation around, and it's like T3 is equal to T4 times P3 divided by P4 to the K minus 1 over K. Okay, so this is the one that we'll use now. So we can solve another problem. So here we have an air standard Brayton cycle operating with 300 Kelvin and 85 kilopascal at the inlet to the compressor. So that's T1 and P1 specified. The compressor pressure ratio is 11, so P2 divided by P1 is 11.0. And the maximum temperature is 1450 Kelvin, so that's T3, isn't it? 1450 Kelvin. On the basis of a cold air standard analysis using this value of C sub V, this value of C sub P, and if you do the ratio, you find that K is close enough to 1.4, 1.399 something. You know, it's 1.4. We'll just use it 1.4. Determine all of these things. So one thing to do is to go ahead and make that sketch. Go ahead and get the temperature entropy sketch. Put your states on there so that you know 1 to 2 is isentropic, as well as 3 to 4 is isentropic, as well as the maximum temperature state 3. You can also make a quick table of state 1, 2, 3, 4. Talk about the pressure in kPa, talk about the temperature in Kelvin, all right? Because it's a cold air analysis, anytime we need to change in H, we'll just use one of those specific heats, C sub P times delta T, true? Yes, sir.
Sir, what is it again for the cold? What is the purpose of studying cold air standard analysis?
Well, with the air standard analysis, are those things where we replace, it's only air, it's never CO2 and water vapor, and we replace the intake exhaust by a heat exchanger, and then we replace the combustion by a heat exchanger, those things for the air standard. Now with the cold, that's an additional assumption that we're going to use constant specific heats evaluated at room temperature or atmospheric ambient temperature. Even though the temperature is spanking hot at state 3. It's up at 1450 Kelvin. We'll just use it around 300 Kelvin. And when you do a cold analysis, you get that analytic expression for the thermal efficiency. Just like we got for Otto and diesel, you can get the analytic expression for the thermal efficiency of the Brayton cycle. So let's go ahead and put in here 85. And 300. How do I get pressure at state 2? It's not 85 anymore. What is it? You multiply by the pressure ratio of 11, true? So if you multiply by 11, you'll get some number. So this is 85 times 11. Okay. How about the temperature at 2? How do I find the temperature at 2? Well, we just wrote that equation down, didn't we? It was just, it's right here. You use this analytic expression, and you apply it for the compressor, and that's how you get the temperature at state 2. True? Okay. So you get, I'm going to call it T2S. Now, how about the pressure at state 3? It's the 85 times 11. So you get the same pressure. It's the same. They're the same. How about T3? Well, that was specified, 1450. That was given as our maximum temperature in the cycle. And then the pressure at 4, you're back down to the pressure at 1. And you do isentropic expansion, T4S. And the equation for T4S, we just did it right here. True? So it depends on K and the pressure ratio. So for part A, the temperature at the compressor outlet, that's T2, is equal to whatever T2S. How about for B? Peak pressure. That's almost too easy. That's P2 is equal to P3 is equal to 85 times 11. How about C? Temperature at the turbine outlet. Isn't that T4? And that's the equation we just had for T4S, that expansion through the turbine. How about D? The heat addition in the burner. So this is where we have our heat addition from state 2 to 3 in the burner. That heat exchanger, sometimes you call it a burner. So what is that Q in? It's going to be H3 minus H2, and because of constant specific heats, we put C sub P, T3 minus T2. True? So that's how you would calculate it. Now, let me ask you a question. Well, let me continue on. What is the net work for the cycle? W net. You can do just like before. You can get it WT minus WC, or you can get it Q in minus Q out. I recommend the first time through, do it both ways. And then get a lot of confidence in your calculations, right? So if you do it this way, you have to get what Q out is. Here's Q out as a positive Q out. Because I put the negative sign right there, I'm treating Q out as a positive quantity. And so Q out is, this is state 4 right here, is C sub, well, maybe write it in terms of H's first. H4 minus H1, so it's C sub P, T4 minus T1. Once you have all the temperatures, boom, you're getting all of them. So that's how you then calculate the net work for the cycle. What about F? The thermal efficiency. It's the net work. That's the answer for part E divided by Q in. The answer from part D. True? And then G, the back work ratio. Well, here you need to get the work of the compressor and divide it by the work of the turbine. Here's a question now. Did we ever use C sub V? Never. Why'd they put it in there?
Well, you could use it to calculate K, but that's in the table anyways.
To use it to calculate K, but it's in the tables anyway. And just so if a student started to use C sub V for, I think Q in is a change in U's. Well, you just threw away a bunch of points. True? So, there you go. Any other comments or questions about this problem? Does it look straightforward? You think you can do that? Derive the equation for the thermal efficiency of the ideal Brayton cycle, assuming a cold air standard analysis. So this is that equation. It's the thermal efficiency. And it's really interesting that you can get it wrapped up, I know there's some assumptions behind this equation, to such a simple expression. It's just the pressure ratio and K. And K is typically just 1.4, because that's what you would deal with, cold air. So it's just a function of pressure ratio. Isn't that almost mind-boggling? The first time you see it, it can't be that simple, but it is. It does work out to be that simple. So if you want to derive this expression, do this. Go ahead and construct a temperature entropy diagram. You do it enough times and then you get really good at it. True? Remind yourself what's happening between each of the states. Put in even a little diagram. Compressor, I'm going to call it burner this time. Sometimes I just call it heat exchanger. Turbine, and then just some heat exchanger to close the loop. And put in, okay, this is state 1, state 2, state 3, state 4, right? And the flow goes this way through the system. All right. So the equation for the thermal efficiency, is that equal to the work net out divided by Q in? And is that equal to the Q net divided by Q in? Is that equal to Q in minus Q out divided by Q in, where I am treating this 2 to 3 as Q in. That's Q in to the burner. And a positive Q out, right here, positive Q out. So I'm taking account for that negative sign, Q in minus a Q out. Okay. So this thermal efficiency starts to look like the form of this 1 minus something. True? See how it's 1 minus something? So that's very consistent with the other ones. So if you want to follow, this is 1 minus. What is the Q out in terms of? Is that H4 minus H1? In is that H3 minus H2? Did I do that right? And is that equal to 1 minus C sub P T4 minus T1 divided by C sub P T3 minus T2. Notice that at this point we finally make the use of cold. The cold air, everything else, it doesn't matter if it's cold or variable specific heats. But at that point you assume that, oh, those delta H is equal to C sub P delta T's. The C sub P's cancel, and continuing up here, we get the thermal efficiencies 1 minus, pull out in the numerator T1, pull out in the denominator T2. So you have T4 divided by T1 minus 1 and T3 divided by T2 minus 1. True? All right. If you doodle on the side or go back and remember our equations, put it kind of in this box right here, that T2 divided by T1, it's the ideal Brayton cycle, it's reversible compression, is equal to the pressure ratio P2 over P1 to the power K minus 1 divided by K. We use that, true? Good. Now, the other thing is we have to work with this expression T3 over T2. Well, is that equal to T3 divided by T4 times T4 divided by T1 times T1 divided by T2? Does that look reasonable? And this ratio right here, 1 to 2, is the reciprocal of the line above, true? But also go and look at 3 to 4. And when you make the product of 3 over 4 times 1 over 2, that they cancel, they're equal to 1, and so this result gives me just T4 divided by T1. So T3 divided by T2 is the same as T4 divided by T1. I'll kind of repeat that without doing a lot of the algebra, but this ratio right here times this ratio right here is unity, is 1. Now that we see that, now we can say, oh, well, this is equal to that. And so what the efficiency is 1 minus T1 over T2. Oh, we already know what T1 over T2 is. It's 1 over P2 over P1 to the K minus 1 over K. So that's the result we wanted to show. So there's the derivation. Now, the first time you do it, it probably takes you a little longer to figure out that the product of T3 over T4 times T1 over T2 is equal to unity. But that is true. All right? I'm going to go ahead and stop. Thank you for your attention.